Okay, in this video, I'm going to just talk a little bit about the Milliken oil drop experiment. So Milliken used a set of parallel plates to find the charge on an oil drop. Draw and label a diagram of Milliken's experiment. So what he did is he had a couple parallel plates, and they were attached to a battery. And it was pretty big voltage, so some big stack of batteries like that. And then we put a little oil, he sprayed a bunch of oil drops in it. And some of the oil drops would be too heavy, so they'd fall down to the bottom. And some of the oil drops would be too light, so they'd slurp up. But some of the oil drops would sit right in between the two plates and be suspended. So that's what he did. This is our battery. These are our parallel plates. And these are the oil drops. Now, by making a careful measure of the radius of the oil drop and using the density of the oil, he could come up with the mass of the oil drop, and based on the mass of the oil drop, he could come up with how much charge would be required to suspend it between those two parallel plates. So let's just work through a simple calculation of something like that, where instead of finding the charge, we're going to find the mass of the suspended particle. But you'll be able to see all the mathematical relationships that are involved in that. So if the charge on the oil drop is 8 times 10 to the negative 19 coulombs, and the voltage across the plates is 120 volts, and the spacing between the plates is 1.2 centimeters, what's the mass of the suspended particle? So what we have to recognize here is if this particle is suspended, then the force of gravity must be equal to the electric force. That's based on Newton's first law. So we're assuming the experiment was done on the surface of the Earth, so we can use the simplified formula for the force of gravity, mg. And for the electric force, we're going to use the idea of the electric field, EQ, and then we're going to recognize that since the electric field between two parallel plates is constant, we can derive this equation, E equals V over D, and that'll be in a different video. So that means that mg is equal to VQ over D. And if I bring the G over, I can say that the mass of my oil drop is equal to the voltage times the charge divided by G and the distance between the plates. Now the only thing I need to be careful of here is I need to make sure I'm putting all of these things in standard units. Beyond that, I should be good to go. 120 volts times the charge on this one, which was 8 times 10 to the negative 19 coulombs, divided by G, 9.8, and the separation, newtons per kilogram, and the separation distance between the two plates, 0.012 meters. So this is just a big calculator work here. 120 times 8 exponent negative 19 divided by 9.8 divided by 0.012, and I have a mass for my oil drop of 8.16 times 10 to the negative 16 kilograms. So that would be the size of oil drop that would have been suspended in that situation. Now let's do a little different thing here, where we're going to use we're going to let this particle accelerate all of a sudden and see what happens. So if the particle is suspended halfway between the plates and the voltage is turned up to 700 volts, what will be the impact velocity of the charge with the top plate? Because the electric field between the plates is constant, I can actually go ahead and use a forces approach to this problem and use my 5 equations of motion, because with a constant force I'll get a constant acceleration, so that'll all work. So my force here is going to be equal to EQ. And again, this will be my force of electric. So now, again, using the fact that my electric field is equal to V over D, I can say that that's equal to VQ over D. And so I can come up with how big my electric force is in this situation. Let's just go ahead and do that. 700 times 8 exponent negative 19 divided by the distance between the plates, 0.012, I get an electric force of 4.67 times 10 to the negative 14. Because this is an oil drop and not an elementary particle or something like that, I still need to consider the force of gravity. I know that the mass of the oil drop is 8.16 times 10 to the negative 16 as stated above, so if I go mass times g, I get 8.0 times 10 to the negative 15 newtons. So I have a electric force pushing this object up at 4.67 times 10 to the negative 14. And I have a gravitational force pulling it down at 8.0 times 10 to the negative 15. And my screw. So what happens to this from every now and again is it overheats. Okay, sorry about that pause there, but I think the computer thing overheated a little, so it got frozen, but it's working again. So my net force here is obviously going in the upward direction, 4.67 exponent negative 14 minus 8 exponent negative 15, which is 3.87 times 10 to the negative 14. That's my net force. Now I have the mass of my oil drop there, so I can use F net equals ma, Newton's second law. So dividing by 8.16 exponent negative 16, I get an acceleration of 47.4 meters per second squared. So we had this oil drop that was suspended halfway in between these two plates. So we're going to assume his initial velocity was at rest. He's then accelerating at 47.4 meters per second squared, but it's over a very short distance, so it's not going to be all that effective. If the total distance here is 0.012 meters, he's only accelerating over 0.006 meters, half of that. So we have a distance of 0.006 meters. The question is, what's his final velocity when he hits that plate? So because the acceleration is constant, we can use our 5 equations of motion. So I'm getting a V2 here of 0.75 meters per second. Let me just hit that one more time, make sure. Yeah, 0.75 meters per second. So that's how fast it's going to go when it hits that top plate because we increase the voltage.